Hello, everyone. I am Nicola Draghi, and I prepared this presentation with my colleague Taylor Morrison that will present the energy balances presentation later on. So I'm an energy data manager here in the agency. I work at several annual energy statistics work stream related to several fuels and countries. And I want to give you an initial presentation to provide a brief overview of the fundamental concept in energy statistics here that will be useful for the later the following of the training. So energy data can be used for a variety of different purposes, such as tracking and understanding energy supply and demand trends, generating energy balances, and we will see that later, but also indicators, reviewing energy security, understanding energy access, and also informing and evaluating policy design. So the products that we use, the flows that we examine and that we want to show, and in general, the issue that we face are common across countries. So it's very important to have comparability indeed between countries and to speak the same language and to have common terms, definition, and also methodologies in data collection and dissemination. So at the IA, our reference is the International Recommendation for Energy Statistics, also called IRES, that you see here. And this is an internationally agreed set of recommendations adopted by the UN Statistical Commission in 2011, and indeed that was agreed between several organizations, among which the IA, the UN Statistical Division, and many, many others. And it aims to ensure cross-country comparability of data by providing common standards and guidance to energy statisticians on concept, definition, and methodology. You have the link here below. You can find it easily online, but you have the link here below in the slides that you will receive later on. And IRES have been translated into 6 different languages. So let's now look at some key concepts referred to IRES. And here we have this concept that help us to define the scope and also draw the boundaries of energy statistics, because as you know, energy is observed all around us in various forms, for example, light, heat, chemical energy, kinetic energy, electrical energy, and so on. But not all the energy is included in energy statistics. So generally speaking, energy that doesn't have a direct impact on society is not measured or monitored as part of energy statistics. So this means that we have some boundaries around which we consider what is inside and outside energy statistics, and IRES with its definition help us drawing these boundaries by producing and giving some common concept and definition. These include, starting from the top of the page that you see here, the definition of energy products, which are form of energy suitable for direct use. This can be coal, oil, gas, electricity. They are based on the SIEC classification that we'll be seeing later on, the Standard International Classification of Energy or Energy Products. Then we have energy flows, which are the activities that we track in energy statistics and that are undertaken on a national territory regarding energy products. So they concern the production, the trade, and the consumption of such energy products. And again, we have a reference, a classification, which is ISIC, and it's called the International Standard Industrial Classification for all economic activities. Then production, so the third here, the third one from the top, production. This is a very important concept, and indeed we will deepen its definition later on. But for now, we just want to say that it concerns the production. It's the starting point of the energy that enters energy statistics. And again, it concerns the production of energy and energy products by any economic unit, including household. And we will see the differentiation between principal and secondary activity and whether this energy is sold, used, unused, or delivered, and so on. Then we have the energy sector, that it's a very important sector. And It's also very important, its definition, because it's the sector where the principal activity is indeed the production, transformation, or distribution of energy. And this sector is considered separately from the final industrial consumption sector and the other final consumption sectors. And finally, we have the concept of reference territory, which in energy statistics concern all the energy activities that physically take place within the national territory of a country, regardless of the nationality or domicile of the people, of the actors or the economic activities that is doing that. So this differs, for example, from the residence principle, which is used in other statistical systems and which look at the domicile and not at the geographical location where the action happens. Now, briefly touching the products which are used in our energy reporting. They are based again on this classification by SIEC that arranged them in a statistical classification. And this system, it's called indeed SIEC, that stands for Standard International Energy Classification. What is very important is that IRES and SIEC also show the links and the correspondence between different classifications. So on the right side, you have, for example, the CPC, the CPC, and the HS. And for what concerns SIEC in IRES, you see the table. There are 10 broad categories of products that we just put here, and we see here coal and just coal for the moment. The other are farther below in IRES. But there are 10 of them. They can be coal, they can be natural gas, oil, electricity, and so on. And this broad section are then broken down into individual products or classes. And here we saw that much better. Maybe let me actually magnify it and highlight it. So coal then it's divided in several subproducts that can be primary or secondary products that are in this case anthracite, coking coal, other bituminous coal, and then we have some other here as coke oven coke, gas coke, BKB that are secondary products. And coming back to the full slide, perfect. So as mentioned, IRES was adopted in 2011. So some time has passed and the energy landscape has changed from them with new products that are emerging, such as green hydrogen and ammonia, which means that SIEC needs to be rejuvenated, let's say. So it's currently undergoing a revision, and following that, an updated version will be released in the next couple of years. Now, let me touch very quickly the energy balance, because Taylor later on will show it with many more details and many more explanation about its convention and what it represents. But let me say here that the energy balance gives a great picture of the energy situation of a country. And again, not giving too many details, but I want to just show you that it's divided into 3 main blocks that you see here. So at the top, there is the supply blocks that indeed concern the supply of a given energy product, or in this case, all the energy products that are here in the vertical dimension for this country. Then we have the second block that includes both transformation and energy industry on use. And for transformation, we intend all the flows where there is a transformation of one type of energy or one energy product into another. And then we have final consumption over here, and we will go through this block separately. And transformation, energy industry and use, and final consumption constitute what we call demand. Now, looking more closely at the supply, and we do that in order to present some specific flows later on that will be very, very useful, the definition for later understanding the rest of the training. We see that it presents just some broad high-level flows as production, trade, bunkers, and stock change. So it gives us already a good starting point for looking at the energy picture of the country, because we can see the relative importance of different products, whether the country is a net importer or exporter for a given product, but also in total. and in particular the TES row that it's circled in blue over there and stand for total energy supply, allow user to see the total amount of energy available for domestic consumption in a country and the relative contribution of each fuel, so that you can easily see which fuel is more important for the country. And also, if you do a bit of further analysis, for example, you can look at the self-sufficiency for a given product or the total one for the country. Now, I want to look at the production flow that we said before. It's the starting point of energy statistics, and it's very important. So for primary products, which are extracted from the biosphere and from nature, then the quantities reported in production are those accounted after cleaning. So they are the ones that are ready to be sold. For example, let's look at coal. And the quantity reported in production for coal are not the total amount directly extracted from the soil, which might include gravel or rocks, but it's the amount that is available after the cleaning. And we see here in the slide the removal of some inert matter, for example. It's important to notice, and we have highlighted here in this phrase and over here, that on the production side, also the quantities that are then consumed by the producer in the extraction process, for example, for heating, for powering the manufacture and equipment used in production, they are included within the production amount, because they are reported, they are definitely an energy use, and they are reported later on the demand side in the balance. I see that we have one raised hand. Maybe I will keep the presentation, and I apologize to Wojciech for that. And maybe you can write the question in the chat, or we can just go to that right after when I finish the presentation. And for natural gas and oil, that it's the other example that I want to show here. You know that often we have quantities that are reinjected, vented, or flared for operational purposes. So, and also we have in the gathering center, again, the cleaning of the extract matter to remove impurities and so on. So again, these amounts, the ones that are flared, vented, reinjected, or just taken out from the mainstream because impurities, they will not be part of the marketable production that it's reported in energy statistics. Let me say that this important concept applies also to renewables that we didn't put here in the slide. In particular to physical primary renewable and waste energy product. But for those, the most important concept to remember is to report production, for example, primary solid biomass that is used only for energy purposes, which means to report the amount of primary solid biomass that is going to be combusted, and then the heat or the electricity produced is going to be used in some way that it's important. It's used in the society. Let's say, for example, waste heat, which are combusted just to reduce the size. So, for example, in a landfill, open air burning, that is not included in energy statistics because then the heat is not reused somehow. Another thing that I want to say about production is that biogases and liquid biofuels for convention are considered primary products, which means that the border of energy statistics stop at their indigenous production and does not consider all the feedstock that is used to produce them, although some of these might fall into other energy product categories. So now let's look at another important concept of the first block, which is trade. And for physical energy products, we consider imports those quantities entering a country for them being used within the country, while export will be those amounts that have been domestically produced but then leave the country and will be used in other, obviously. This means that transit trade is excluded, and you have here some example that you can see also at home, but the one that are more problematic would be for country B and C, where it depends on the amount of imports and export, for example, for country B, to know whether there is transit trade or not. And for country C, where there is no production, there are imports and export, it's very likely that there is transit trade going on, but there can be also some specific situation where, for example, exports are drawn for stock change. So in this, let's say, limit cases, we always ask energy statistician or ourselves as well to you to know as many details as possible, to know what's really happening, so that we can see whether, for example, in this case, it's about transit trade, so it should be excluded from energy statistics or not. Now, there are two exceptions. The first one is electricity and heat, where there is no transit trade, but instead trade is reported on the basis of border crossed and not origin and destination. So trade includes the amount in transit. Here we have the example of, over here, the example of, for example, a French big consumer that buys electricity from Portugal, from a Portugal producer, but since they don't share a common border, we will not have France reporting imports from Portugal, but we will have instead a series of imports and export where Portugal export to Spain, Spain report imports from Portugal and exports from France, and France will report imports from Spain. Another exception is for liquefied natural gas, where it depends on the country where the energy is regasified to be the country of origin of the imports, and not the country where the natural gas was produced or and liquefied. So let me highlight another flow for the first block. And this flow is the international bunkers. They can be marine and aviation. Sorry. So this flow is very important because a big amount of oil products, and in recent years also of natural gas, in their overall balance is used for this transport and these international voyages. And we need to account very well between international and domestic voyages for emission calculation. Now, the first thing important to distinguish here is between domestic and international voyages. And the split is done on the basis on the port of departure and arrival. You have the definition over here, and not, for example, on the flag, and for a single voyage. Then we have the accounting in the energy balance of a given country, and that depends on not on the flag of the ship, but on the port of departure of the vessel. So if a ship has whatever vessel, let's say I'm Italian, so let's say a ship that sails from the port of Geneva and has a French flag, then because it sails from an Italian port, it means that it has refueled there. So the fuel that is used there, it's then subtracted to the domestic supply of Italy as a country. So it should be reported into the energy balance of Italy. Now, moving to the second block, and I will be fast here and go again into specific concept later on. Now, this is the block where the most important flows are the transformation flows that refer to the conversion of one form of energy to the other. So you have the production of secondary sources. I will not go into the details of the convention. That will be somehow explained later on by Taylor. But for example, we have here electricity plants where there is an input of coal reported with a negative sign and an output of electricity reported with a positive sign. Now you see that the output of electricity is very big. So this is actually the output from the overall inputs of all the products. And in the total column, you see the losses of the process, because obviously the process has an efficiency that it's less than 100% when you speak about conversion to electricity from the combustion of fossil fuel, but in general, all the transformation efficiency will be less than 100%. It's important to say that in this block, we have also energy industry on use that was here. Now this is an aggregated view, so you will have many flows also within the energy industry on use flow, let's say. And let's look at their definition exactly here. So the difference and the distinction between transformation and energy industry on use. So we have here, for example, an oil refinery where crude is transformed into secondary oil products that can be whatever, gasoline, diesel, fuel oil. And crude oil, when this happens, transformation into a secondary oil product is a transformation input, while the oil products are the transformation output. However, the refinery can be used some still crude oil, but more generally some secondary product as fuel oil, residual oil, for running, for providing energy to their own operation, lighting, heating, power, and so on. So this fuel is not a transformation input, but it's categorized separately into energy industry on use. And indeed, in a fully disaggregated balance, you will see similar flows both for transformation and for energy industry, so a sort of duplication. But now you know that they correspond to two different processes, one transformation and one energy industry on use, and that's why they are duplicated, and you can see transformation in our refineries and energy industry on use in our refineries, but they refer to different concepts. Now, briefly, let's look at transformation efficiency. And they are calculated as the total energy of the outputs of a transformation, of the total energy of the energy products, which are the outputs of a transformation, divided by the energy content of the input fuel or fuels. In this case, a simple transformation is again the production of electricity with the input combustion of two fuels, A and B, and the efficiency is simply C divided by A plus B. But it's very important to remember that here C, A and B must be on the same energy unit and the same energy form, net or gross. Here we go. So the efficiency is never larger than 100%, and its expected range will vary depending on the process, on the fuel, on the technology, and so on. But efficiency can be a very useful check for the commodity balance of the products involved in a transformation. And this check can be very useful if you compare the efficiency in a given year with the historic efficiency or with the expected range for similar processes also in other countries. For example, if for a given country you have a oil refinery that has an efficiency of 50%, it means that there must be some problems with data availability. And there are either some oil products that are missing, most probably, but it could be that also you have too much crude oil input that has been reported as transformation inputs, where instead it could be used somewhere else. Now, let's move to the concept of electricity and heat production. And when we speak about that, we need to distinguish between two types of producer, which are main activity producers and auto producer. Main activity producer are the ones that generate electricity and heat for third parties as their primary activities. So the main goal is to generate and sell the electricity and heat they produce. And a nuclear power plant is a good example for that. By contrast, auto producer generate electricity or heat only as a secondary activity in support of their primary activity. So this can be the case of large industrial facilities that consume a lot of energy, that do not want to rely maybe only on the grid if there are some blackouts and so on. So they have also on-site power plants that produce energy for their own processes. So this energy is auto-consumed, and some can also be sold in some cases. And this will be called auto producer. And it's important to notice that ownership is irrelevant. So the difference between main activity and auto producer, it's based on the primary activity and not on the fact that they are, for example, public or private companies. And obviously they can generate only electricity, only heat, or both of them. Now, based on the fact that they're main activity producer or auto producer, the reporting of the electricity and heat generated, but also the corresponding input can vary, and there are some convention. So for main activity producer, it's very easy. We report all the production and all the input. For auto producer, when we are speaking about electricity, we report again all the inputs and the outputs, whereas for heat sold, only the amount of heat, for heat produced, but also auto-consumed, we only report the amount of it which is sold. So if, for example, an auto producer produce 100 units of heat and consume for its own purposes 70 of these 100 units and sell only 30 of these units, only the 30 units of heat would need to be reported, whereas the other 70 units of heat will not be reported anywhere. For what concerns the associated fuel inputs, also here, only the amount of fuel input associated with heat sold are reported. So only the amount of fuel associated with heat sold are reported in the fuel balance into auto producer heat only or CHP, whereas in this case, instead, the amount of heat that is burned to produce, the amount of fuel that is burned to produce heat that is auto-consumed will be reported in still in the fuel balance, but in final consumption in the corresponding sector associated with the primary activity of the auto producer. We can look at this topic also later on if it was a bit confusing and too fast, this explanation. But then we have the last block here, which is final consumption, and it's the deliveries of energy product to all final consumers in all the sectors. So we have industry, transport, residential, commercial, and public services, and so on. So the data here on the left side are aggregated, but in the balance, in a disaggregated energy balance, we have many subflows that can be all the industry, different subsectors, road transport, rail, and so on. And it should be noted that in IRES methodology, transport is a cross-cutting sector and it's not linked to an industry. So for example, the fuel used to move a truck that transport a given product related to an industry, for example, iron ore that is used then in iron and steel industry, it should be reported that fuel use under transport and not under iron and steel. Finally, quickly, for liquid biofuels, it's very important to avoid double counting with the corresponding liquid fossil fuel they might be blended with. So in this slide, we see how we treat this topic when data collection is made in questionnaire, like renewables and wastes and the oil questionnaire. And this is what we have, this data collection with some countries. And in the renewable questionnaire, we report only production and consumption of pure liquid biofuels. So this means that you don't have to report the portion of biofuels blended with oil products because they will be reported directly in the oil questionnaire. And this concept applies also to biogases when biogases are blended with natural gas. And as I told you before, you will have this slide at the end of the presentation and you can read the example with more calm. Finally, we arrive to non-energy use, and it's important to note that we include demand of fossil fuel derived energy products used for non-energy purposes in energy statistics, and this is because in their production and supply is indeed included in the first block of the balance. So we have to account on the demand side for their non-energy uses. But it's important to report them separately from the energy uses because these affect CO2 emission calculation that are based on energy statistics. For example, some of these non-energy uses of fossil fuels are bitumen that is used for paving roads, natural gas that is used for fertilizer production, and oil that is used for producing petrochemical or plastic. By convention, energy statistics used not to include the waste or biomass used for non-energy purposes. So for example, the wood that is destined for construction, for building a house, as I said at the beginning, or for furniture, was not included in energy statistics. However, from this cycle, with the country that report to us the renewable questionnaire, we started collecting non-energy uses of some renewable products where these uses substitute the non-energy uses of fossil fuels, as for example, some primary solid biofuel that can be used to make bioplastic and some liquid renewable fuels that can be used in the petrochemical sector. Perfect, and here the small icon. So to recap, this is again the summary, and it's somehow similar to the energy balance, but in a horizontal dimension. You have all the flows, and on the left side we have the supply side, and on the right side we have the demand. So this energy balance in theory should be aligned in a perfect world. So the number on the supply side should match the number on the demand side. But this in the real world, it's very difficult to achieve because there are issues with data availability, data quality, measurement errors, difference in sources, and indeed every flow will be reconciled, will be taken some time from different sources, and all the balances are reconciliation of different sources. So as a result, supply and demand may differ, and we have that the balancing item is the statistical difference. This is a very important item because highlight the data quality and availability. So ideally it should be as small as possible, and a larger statistical difference implies that there are some data quality issue that should be investigated, but can also be a good indicator of where the problem is, if on the demand side or on the supply side. And on the other hand, also very much care should be taken when we see a zero statistical difference that can imply a low, either a high data quality, but sometimes also not a very high data quality or a data availability problem, because it can be that in some cases we have zero statistical difference because some values in the balance may have been estimated by being set equal to the difference between supply and demand and creating an artificially zero statistical difference. Okay, so we move quickly to conversion factor, and the fact here that there are many different units that we will encounter, and we can measure products indeed in mass, in volume, and in energy units. So we will have often the need to convert from one type to another, and when the conversion is within the same category, this is generally easy because it's based on a constant. For example, 1 gigawatt hour will be always equal to 3.6 terajoule of energy, and 1 ton equal to 1,000 kilogram. However, then we have, let's say, some problems or more difficulties. We have to convert between different categories. So here you have mass to volume, but even more importantly, mass or volume to energy, because then you need some specific conversion factor, which are especially for when we do mass to volume, mass or volume to energy, they are product specific calorific value. And since the energy balance is based on energy units, but often the energy products are collected in physical units as tons, as cubic meters for natural gas, and so on, to produce an accurate energy balance, we need accurate data, not only for the physical quantities, but also for the specific calorific values, especially when we are speaking about more heterogeneous products. So this is again an example of the importance of calorific value, which are used to convert physical unit into energy units. And calorific value represent the energy in the form of heat released when the fuel is combusted. So we have a small example over here where we see the importance of calorific value, because it might be that the same product, bituminous coal, which is very heterogeneous, might have a calorific value in one country and a 50% higher calorific value in another country. So if, for example, in country B, by mistake, we used to calculate the energy amount of a given quantity by using the calorific value of country A, we will have a 50% underestimation of this quantity, and vice versa. So it's very important to collect specific calorific value, not only by product, but also by flow and year, obviously. So I will skip this small example that you can find later on in the slide, and this that was only related to the calculation of these calorific values. but we will see that also later on. And I will conclude with just a few final comments on the benefits on collecting energy statistics. So these are reliable, accurate, and timely energy data are very important for policy makers to enable sound, evidence-based decision making. So they can include the development of energy policies as green growth, energy transition, and so on, but also enable the monitoring and reaction to energy security developments such as supply shocks. And then we can also have several other areas of interest that are development, energy access, health, environment, emission, and clean cooking. And in addition, energy statistics can be used for international collaboration and benchmarking, and also by the general public to raise awareness, to be informed, and to understand the energy usage and the energy balance of your own country. So they can be combined with basic energy data. Basic energy data can be combined with various other data sets, socioeconomic as population and GDP. And you have here some example in IRIS, which are really small to read right now for you, but trust me, there are energy intensity indicators and that give the amount of energy in a given sector, or there is the fuel shares in the energy and electricity sector and the energy use per capita and so on. And by doing this combination, you can generate a variety of interesting indicators that can show you different perspective. For example, here we have on the top total energy supply per capita, and on the bottom total energy supply per unit of GDP, and considering from 2000 onwards the evolution. And considering that both population and GDP have increased per se since 2000, we see that these two charts highlight the decoupling between economic growth and energy usage. And finally, our data are also used later on to produce CO2 estimation using greenhouse emission factors and methodologies provided by the IPCC. And lastly, very last slide, in conclusion, beyond high-level data, we can also zoom in and collect some very disaggregated data to highlight specific concepts. For example, residential use here can be broken down into different specific sectors as uses, as lighting, space heating, space cooling, and this information can be very useful to produce more advanced energy efficiency indicators that are more effective to track the success of specific policy. And this means that sometimes we need to collect more detailed data with different templates or running specific survey. So for an energy statistician, it's important to periodically review our data requirements to ensure the continuing relevance of our energy statistics. So that's all for this presentation. Thank you very much.